Hello everyone, welcome to the video series on Target GPAT 2022 MCQ series. In this video, I am going to explain about organic chemistry concepts that are tested in previous GPAT question papers, and this is part 2. I have already made part 1. This is my YouTube channel. If you like the video content, do share and subscribe the channel. Let's get into the topic. Now, choose the most basic heterocyclic compound among the followings. Now, this is a concept-oriented question. You need to know the structures and as well as theories of acid and base. Now, this is the structure of pyridine, a 6-membered ring, right? Imidazole, a 5-membered ring with 2 nitrogens. Pyrrole is the simplest 5-membered ring with this structure, right? Now, this pyrrolidine is a different molecule. Pyrrolidine, see, among all the heterocyclics, this pyrrolidine do not have any aromaticity. Now let us understand the question again. It talks about heterocycle with most basic characteristics. Now in this sense, the moment you see basic means it is because of, you need to consider Lewis theory. According to Lewis theory, electron pair donor is a base. So in order to act as a base, electron pair availability should be there. Now among all these heterocyclics, pyrrole do not have this electron pair because it is involved in delocalization. So pyrrole is an aromatic compound in which the lone pair of electrons are involved in delocalization. So lone pair is not available, it cannot act as base. So this is completely ruled out. Now in case of pyridine and imidazole, yes, they have lone pair of electrons availability is there. But out of these two, imidazole is more basic. It is almost 100 times more basic than pyridine. The reason is, if these electron pairs are donated, it generates a positive charge which can be neutralized by this nitrogen electrons. So there is an additional neutralizing factor is there, whereas in pyridine it is not possible. Though pyridine is basic, imidazole is most basic. Now coming back to the pyrrolidine. See, pyridine, imidazole, both of them has got basic properties, but the basicity is not as strong as pyrrolidine. The reason is, in pyrrolidine, the lone pair of electron availability is there which can easily donated and act as a very good base, electron pair donor. In case of pyridine and imidazole, though they can donate electron pair, this delocalization has got an electron pull which will reduces the electron donating ability of this lone pair. In both the aromatic ring case, the electron pair donating ability is reduced because of aromatic property, whereas such kind of aromaticity is not seen in pyrrolidine. So which one among all these heterocycles is most basic? It is pyrrolidine. You need to understand the concept and basic. You need to know the heterocycle structure and the concept of basicity. Now moving to the next one. Now in Diels-Alder reaction can be carried out in which of the following heterocyclic compounds most readily? Now we need to understand about Diels-Alder reaction. See, Diels-Alder reaction can take place between two compounds. They are known as dienes plus dienophile. So dienophile means, see, di means 2, ene means double bonds, right? So you need to have something with a 2 double bond, a double bond one, and dienophile means an agent which goes towards these double bonds. Phile means like. So all the heterocyclics can act as diene, but again they need to have a very good double bond character. Then only they can act as a very good diene. Then it could easily, most readily go with Diels-Alder reaction. So in order to act as a very good diene, see, all this heterocyclic has got aromaticity. The moment you have aromaticity, the double bonds are delocalized. When they are delocalized, they will not have a very good diene property. Why? Diene means you need to have a double bond character. But when you see delocalization, it will not act as a double bond, rather it is the electrons are revolving. So out of all this heterocyclic, our job is to find out the heterocyclic with lowest aromaticity. Now this thing I have discussed in a previous video too. Among all these heterocyclics, the heterocycle with lowest aromaticity is furan. Why furan? Because furan has got oxygen heteroatom is there. Now though oxygen has got 2 lone pair of electrons, oxygen is very good electronegative atom. It has got 3.44. The moment electronegativity is increased, what happens? Delocalization is decreased. If delocalization is decreased, it will have low aromaticity, and these double bonds can act as a very good diene. So among all of them, the lowest aromaticity is found with furan, and it can act as a very good diene, and it can most readily give diels-Alder reaction. So the answer is furan. So remember one more thing, among all these heterocyclics, the lowest aromaticity is seen with furan. Moving to the next one. Now read the following statements carefully. See, Pyrrole, thiophene undergo electrophilic aromatic substitution reactions much faster than benzene. This is true. The reason is, see, benzene has got 6 atoms and it has got 6 electrons. So every atom has got 1 electron. Whereas Pyrrole and thiophene, they have got 5 atoms but they have 6 electrons. So they are known as electron rich. The moment you see electron rich, electrophilic aromatic substitution goes faster. That is the reason why all 5-membered heterocyclic rings, electrophilic aromatic substitution goes faster than 6-membered rings. So this is true. P is correct. Moving to the next one. Now, Pyrrole, thiophene undergo diels-Alder addition reaction very fast. No, just now we have seen it is only with furan. This is not true. Now, Pyrrole, thiophene undergo nucleophilic aromatic substitution. No, these are electron rich. Electron rich means electrophilic substitution will take place, not the nucleophilic. This is wrong. Now, Pyrrole is a pi excessive system while thiophene is pi deficient. No, both of them has got 5 atoms and 6 electrons. Both of them has got equal pi system. So this is not true. So among all these things, only option P is right and QRS are false. Now you need to write the combination. See, P only is true while QRS are false. So this is the answer. Moving to the next one. Now, given are the 4th statement about dehydration of alcohols to give alkenes. So this is what is dehydration of alcohols to give an alkene. Now look at them. Ease of dehydration of alcohol takes place in order of tertiary is greater than secondary is greater than primary. True. Why? Why? Because when this OH comes out, it forms a carbon with a cation. Carbocation stability is in the order of tertiary is greater than secondary is greater than primary. So the ease of dehydration follows the pattern. This is true. Second one, dehydration is acid catalyzed. True. Why? In order to make this OH as a good leaving group, a proton is added and it comes out easily. So this is also true. Dehydration is catalyzed, is acid catalyzed. Now next one, orientation of alkene is formed strongly, Said-Jeffs rule. Now Said-Jeffs rule predicts that the most stable products are highly substituted around this double bond. That is what is Said-Jeffs rule. Yes, the orientation is according to Said-Jeffs rule. Now dehydration is irreversible. No, it is reversible. So this is not correct. So we need to figure out the answer. So except S, all of them are true. So PQR, no. PQR, all 3 are correct, but S is not. This is the right answer. So again, this is a concept-based question. Moving to the next one. Now read the following statements about SN1 reaction. See, SN1 reaction, unimolecular one. First a leaving group goes, forms a carbocation and a nucleophile attacks and you will get final product. Let us see. See, SN1 proceed with complete inversion. No, this Walden inversion occurs with SN2, not with SN1. Next, they proceed with racemization plus some net inversion. This is true. What do you mean by this? See, the incoming nucleophile can attack from this side or from this side. From this opposite side, it results in net inversion, whereas some of the nucleophiles can come and attack from this side. So you will get a mixture of both the isomers, like racemization is there, net inversion is there. So this is true. Now, they are characterized by rearrangement. This is true. What do you mean by rearrangement? The moment you say rearrangement is possible whenever there is a formation of carbocation. See, this carbocation, carbocation stability is according to tertiary is greater than secondary is greater than primary. So if there is a primary carbocation, it can rearrange as to tertiary. If secondary is there, it can rearrange as to tertiary. So rearrangement is always possible. This is true. Now, next one. They are characterized reactivity sequences. This no. Just now we have seen about rearrangement. Rearrangement is in the sequence of tertiary is greater than secondary is greater than primary. So this one are not true, whereas the Q and R statements are true. So we need to figure that combination. See, Q and R are true while P and S are false. This is the answer. Again, this is completely based on SN1 reaction mechanism. I have made a video on nucleophilic substitution reaction. Please watch it for detailed mechanism. Now, determine the correctness or otherwise of the following of assertion and reason questions. These are interesting ones. Look at this. Halogens are unusual in their effect on electrophilic aromatic substitution. They are deactivating yet orthopara directing. See, on the benzene ring, if we have electrophilic aromatic substitution will take place. Now, If something is donating electrons, it will be considered as activating, and activating groups are usually ortho-para directory. But halogens are unusual because they are deactivating, because of their electronegativity, they withdraw electrons and they act as deactivating. Still they are ortho-para directory. Why they are ortho-para directory? Because halogens has got lone pair of electrons which are donated to the ring, so it causes orientation to ortho-para. So you need to understand two effects. Inductive effect is deactivating, whereas mesomeric effect is ortho-para orientation. Now, the reason given is here is in electrophilic aromatic substitution reaction, reactivity is controlled by inductive effect. This is true. Orientation is controlled by hyperconjugation. No, it is controlled by mesomeric effect. So A is true, but reason is wrong. Let us see. See, A is true, but R is false. Yeah, this is bingo. This is the right answer. So R, it is not hyperconjugation, so it is mesomeric. So this is correct option. Moving to the next one. Now, which of the following is not a bioisosteric pair? See, bioisosteric pair means in medicinal chemistry, you can replace a group with another group which has got similar chemical and physical properties. The moment you say chemical properties, it should have similar electronic configuration. Let us see about this. Carbon, nitrogen, oxygen. See, I am just writing the periodic table order. Now look at this divalent ether. Ether, see, let us see the valency of these atoms. Valency of carbon is 4, this is 5, this is 6, this is 7, right? So when you take oxygen, it can be replaced by nitrogen plus hydrogen. Why? Nitrogen valence is 5 plus hydrogen valence is 1, so it is equal to 6. This is what happens with bioisosteric pairs. Now hydroxyl and thio. Now oxygen, sulfur, both of them belong to the same group. So they have similar electronic parameters. So OH can be substituted by SH. This is also true. Now hydrogen and fluorine, yeah, both of them has got 1 electron, so they are also electronic isoelectronic pairs. But the odd man out is carbon dioxide and sulfur dioxide. No, carbon is this one, sulfur is this one. They cannot. So this is wrong. So not bioisosteric means C. Moving to the next one. Now chloroform stored in dark colored bottles because it is oxidized in presence of light and air to a toxic compound, that is phosgene, COCl2. It forms phosgene under the influence of oxygen and light, so it has to be stored in dark colored bottles. Going to the next one. Arrange the following groups according to the sequence rules. See, sequence rules are given by Kahn, Ingold and Pyrrole. So according to the sequence rules, see, usually it comes with optical activity or asymmetric carbons. Let's say you have an asymmetric carbon and it is surrounded with 4 different groups. You need to give priority according to sequence rules. The priority is given, the first rule to give priority is molecular weight. Now look at the groups. The first atom is everywhere, it is carbon. It is same. If it is same, you need to proceed to the next atom. Next atom is oxygen. Next atom is oxygen. So here hydrogen, here a bonded carbon is there. So carbon is prior than hydrogen, but oxygen is more prior than hydrogen. So these two comes first. Now again you have one more oxygen is there. So COH group is like this. So which is bonded to 2 oxygens. So highest priority is given to COH group. Next priority is given to COCH3. In case of these two, a carbon is attached to hydrogen here, whereas carbon is attached to carbon here. Carbon has got more molecular weight than hydrogen. So this one comes 3. And this one is 4th one. So usually the order is like this. A has to be given priority, then B has to be given priority, then D has to be given priority, then C. So this is the right order. So these are called a sequence rule, and they are according to Kahn, Ingold and Pyrrole. The last one. Look at this. The following statements are given. So this is very important, especially related to stereoisomerism. So very important statements, look at them. Conformational isomers are interconvertible by rotation around a single bond. This is true. While configurational isomers cannot be interconverted without breaking a bond. Absolutely true. In fact, these are the definitions for conformational and configurational isomers. Understand them. Conformational, interconvertible, rotation around single bond. Configurational, they cannot be interconverted without breaking a bond. Now next one, configurational isomers could be optically active or optically inactive. This is true. Configurational could be optically active. If there is a meso compound, it is optically inactive. Both of them is possibility. While conformational isomers are always optically inactive because there is a rotation around the bond. So this is also true, absolutely true. Moving to the next one, geometric isomers must have a double bond in their structure. Need not be. Look at the compounds like this. You have cyclobutane compounds like these are there. Two isomers are like this, HCl whereas PiH. Look at them. See, these two are geometric isomers, and these two are geometric isomers without any double bonds. Look at them. So this one is both the bulky groups are on the same time. This is called as cis. This is an opposite term. So these are trans. They are geometric isomers, but they do not have any double bond. So it is not required. This must should not be there. It is not required to have a double bond there. Now next one, geometric and optical isomers are two distinct categories of configurational isomers. Perfectly true, absolutely true. So all these statements are in fact definitions. So remember them. So out of PQRS except R, all are correct. So we need to find that answer. So except R, which one is this? See, P, Q, S are true while R is false. This is true. So these are all the basic things for stereochemistry. You better take a screenshot so that you will understand everything. So this is about organic chemistry concept. If you like the video content, do share and subscribe. Thank you for watching this video.